Listo, profesor.
Now
Okay.
you could start, Professor Stuart.
Thank you, Shimena. Okay, welcome everybody. Buenos dias a todos. Welcome to everybody. We are on LAFMAT now. I would like to welcome the participating organizations. I will list them. We have the National University Mayor de San Marcos in Lima, Peru. We have the University Católica del Norte in Antofagasta in Chile. We have the University of San Sebastian in Puerto Montt, Chile. We have the Centro Atómico de Bariloche in Argentina. We have the Federal University of Pernambuco in Brazil. We have the Federal Rural University in Rio de Janeiro. We have the Federal University Fluminense, also in Brazil. We have the National University of Colombia in Bogota. We have the University del Zulia in Venezuela. University del Oriente, also in Venezuela. And we have the Centro de Estudios de Materiales Avanzados Mexico and Sinvestav in Mexico. So welcome everybody. I am the moderator today, Stuart from London, and I'm going to introduce the speaker today, who is Jonathan Gough. I'll just give a little bit of introduction about Jonathan. Jonathan is a fairly new researcher. He recently got his PhD from University College London. We've been working together now since COVID, really. We started working together in 2020 in COVID, and Johnny has gone on to finish his PhD. And he's going to present some work today that's presently being worked on, and he's been thinking about these ideas for some time. So, Johnny, I won't waste any more of my any more time. We'll get you straight in, and Johnny, it's all yours. So, there we go.
Okay. Well, thank you a lot for that introduction. I'll share my screen now. Okay, minimize this. Okay, hopefully you can all see that. So my talk is titled Low Temperature Activated Transport and Hysteretic Current Jumps in Disordered Indium-Antimonide. So this was work done at University College London, but it was also done in collaboration with our theory partners at the University of Birmingham and also the University of Murcia. And I also wish to thank the Latin American network of condensed matter physicists for this opportunity to discuss the work that we've been doing. Oops. So I'm part of Professor Pepper's research group at University College London. We're involved in semiconductor nanostructure fabrication and low temperature measurements. Our lab is actually based in the London Centre of Nanotechnology on the UCL campus, which is 5 minutes away from King's Cross, so right in the heart of London. So we're fortunate enough to have this lab on the ground floor of the building. So if you've ever been in this area, you may have seen our dilution refrigerators through the windows. So our work can really be separated into three main areas: semiconductor growth, nanostructure fabrication, and low temperature measurements. So typically our materials are grown by molecular beam epitaxy. So this is atomic layer deposition of ultra high quality material. We work with a variety of materials. For example, gallium arsenide, germanium, indium antimonide. So all fairly standard semiconducting materials. We also have some researchers looking into graphene, which are flakes are extracted by exfoliation. So after we receive our wafers, we then fabricate them into a variety of nanostructures. So this can be as simple as a two-dimensional Hall bar, or something as complex as a zero-dimensional quantum dot. So we do all our fabrication in something like this, a clean room. This is our clean room in the London Centre of Nanotechnology. And then we measure our samples within the lab within our cryostat systems. So we have two dilution refrigerators, which have a base temperature of around 20 millikelvin, depending on noise levels. They also come with a 14 Tesla magnet, and we have two dry helium-4 systems with a base temperature of 4 Kelvin and 1.5 Kelvin. So we typically characterize our samples on these higher temperature systems and then cool them down to lower temperatures. So before I talk about the work that I've been doing related to disordered systems, I'm just going to briefly shout out some of my colleagues' work. So one area we're interested in is one-dimensional non-magnetic fractional quantization of conductance. So this occurs in very high mobility samples, so unlike the samples that I'm going to talk about, where essentially you form a 1D channel, say either in a quantum wire or a split gate defined structure like this, and you perform a very simple two-terminal measurement. And it's been known for a long time that you can observe these quantization in your measured conductance due to the number of channels that you, conduction channels that you can fit into this smaller 1D wire. So quantization in units of typically E squared upon H or 2E squared upon H has been known for a long time. The 2 comes from a spin degeneracy of your channels. However, what was noticed 5-6 years ago was that as you relax the channel width, you observe these fractional plateaus, say 0.25 in this case. So one suggestion of why this effect is observed is due to this Wigner crystal formation. So if you imagine you widen the channel, then your electrons can essentially arrange themselves in this kind of zigzag arrangement. So we also have a student looking at quantum pumps. So this would be something like a quantum dot within this area here, which is then separated by 2 gates, an entrance gate and an exit gate. So if you oscillate the entrance gate very quickly, say at an RF frequency, you can load electrons and unload electrons from the dot before they have time to tunnel out. So you observe this quantization in your measured current, which you maybe see on this plot here. So this first plateau would correspond to a single electron being pumped per oscillation cycle, and then 2 electrons, 3 electrons. So it's really an amazing effect that you can resolve this single electron pumping in moderately simple structures. So this has been observed in semiconductors like aluminium gallium arsenide. However, it's currently being extended to graphene devices. So another project that's more related to what I'll talk about is thermopower or electron heating. So this takes place in something like this T-shaped hole bar, where essentially you apply a large current to the T end, which results in a large Joule heating, and then you track how that heat is dissipated along this relaxation channel here. And you track the temperature using Seebeck measurements with these pairs of gated arms. So we're interested in this because in a high mobility system, the electron can travel very large distances without interacting with the lattice where it would lose its heat. However, in disordered systems, you expect that the heat would be lost very quickly. However, that may not be the case for some of the samples that I'm going to talk about. So for the last 5-6 years, the duration of my PhD, and also when I was an undergraduate, I've been working on this area of physics called non-ergodic quantum manipulation. So this really relates to strong disorder, so something called Anderson localization, which I'll explain in more detail, electron-electron interactions, and closed quantum systems. An example of a closed quantum system may be something like these suspended nanostructures, which by suspending them, you remove the interaction with the substrate. So you remove a phonon degree of freedom. You only have these 2D phonons rather than a 3D phonon. At the center of these three areas of condensed matter physics is supposedly this new state of matter called many-body localization. So Anderson localization is often referred to as single-body localization. It's a non-interacting effect. However, many-body localization includes this electron-electron interaction. So it's interesting for a variety of reasons, and a detailed look at many-body localization would need an additional hour to talk about. However, the main property we're interested in is this non-ergodicity. So ergodicity is something that appears in everyday life. If you imagine hot water mixing in your bathtub, eventually the water will reach a single temperature. However, in a many-body localized system, the separate, say, carrier species in this example, would remain separate for an infinite amount of time. So this has given it applications to a variety of quantum technologies, primarily quantum memories. So if you imagine you arrange your qubit state in some arrangement, cool it down so it enters this many-body localized state, your qubit would stay in that arrangement for a large amount of time. So related to this, I'm briefly going to talk about these two observations that we observed in our samples at UCL. These are from disordered materials. So unlike the high mobility structures that we observe the conductance quantization in, these are very low mobility. I'm going to describe the observations in the context of a simple phenological model related to two non-ohmic effects and also this effective granularity. But before that, I'm just going to briefly recap some of the main ideas associated with single body localization or Anderson localization. So like most things in quantum mechanics, Anderson localization can be linked back to the double slit experiment. So many of you will have encountered this in undergraduate physics, but for those who haven't, essentially if you have a single electron source interacting with a double slit with some screen a certain distance away, then over time these single electrons will build up an interference pattern on the screen. So we now know that we can describe this by self-interference. So the single electron traverses two paths simultaneously, and due to the relative phase with this path, which is determined by the separation distance between the slit and the screen, you get constructive and destructive interference. So that's what builds up this interference pattern, where at these destructive interference terms, you don't get this electron sources on the screen. Now, if we take that idea to a disordered system, say we have an electron starting at point R, and it's trying to get to point R prime, and we assume a very simple toy model where we have two paths, these blue arrows, and this red arrow, where here the black stars represent a stationary impurity or an elastic scattering center. Then you'll notice that for each scattering event, the electron will acquire a phase. So as it makes the blue path, it will acquire a phase phi1, phi2, phi5, and likewise for the red path, phi3 and phi6. So when these two paths then intersect, their phase will be completely uncorrelated because by definition, disorder is a random quantity. So this cos term will be averaged out to 0. The average of a cos is obviously 0. However, if we now include this subsect of paths, say clockwise and anti-clockwise around a closed loop, then you notice that the phase associated, or the scattering events, are exactly the same clockwise as they are for anti-clockwise. So the relative phase when these two paths intersect again at point R will be 0. So this cos term associated with self-interference will be maximized. So from this very simple toy model, you can see that these looping paths have an enhanced probability to occur. So this, in essence, is Anderson localization. People often forget that it's a purely quantum mechanical effect. So it's actually been demonstrated in other wave-like systems, like on the surface of water. You can observe this Anderson localization effect under controlled lab conditions. So like the name suggests, it was first thought about by Professor Anderson, where he considered this very simple Hamiltonian, this two-term Hamiltonian, where you have an on-site energy, which is randomly varied to reflect the disorder. The magnitude of the disorder is given by this W term, and then some traversal energy, I. So as we increase disorder, so this top left is the weakest disorder, as we increase disorder here to here to here, you can see that the wave function shrinks. So this is basically due to this looping paths dominating your wave function. So it basically converts your extended states, like a block wave in a periodic crystal, to this localized state where it has this localized envelope over the top of it, given by this localization length. So people often forget as well with Anderson localization, it's not just the wave function that shrinks. The other main result was there exists this ratio between I to W, in 3D anyway, where all states are extended and all states are localized. So this separation between these two regimes is called a mobility edge. Anderson's theory can be taken one step further in a theory called scaling theory, which says that in 1D systems and 2D systems, all states are always localized. So there's not this ratio of I to W, given even the smallest amount of disorder, which is quite an amazing result because a lot of us will be familiar with ballistic wires or high mobility 2DEGs, the type of thing where you observe the quantum Hall effect, so ballistic transport. So this theory essentially says that those states aren't described by block waves, they're actually localized states. But this can typically be a very weak effect given these three conditions. One would be small samples, so this localization length is much larger than the sample size, so you don't see localization. The other might be weak disorder, so the classical terms within the previous slide dominate over the interference terms. And lastly, inelastic scattering. So any mechanism where there's an energy transfer between the electron and another source. So primarily this is due to the lattice, so an electron-phonon interaction, but it can also be due to an electron-electron interaction. So essentially, one way of thinking about this is that due to this transfer of energy between the electron and the environment, you get this wave function collapse, which resets your localization essentially. So you get this scattering rate that's so frequent that you don't observe strong localization. So now if we take this relatively simple example, so we assume we've got a very small sample here, and also we're at low temperatures, so the phase coherence length is very large. So we're increasing disorder from left to right. So at very low disorder, the localization length is much bigger than the sample size. So over the sample, it just appears like standard block waves, as you may be familiar with from undergraduate physics. So transport's most likely diffusive, and as the wave function extends throughout the sample, it behaves like a metal. the zero temperature conductivity is a constant. Now, as we increase the disorder, the wave function shrinks due to the contribution of these looping paths. And we now notice that the wave function is still bigger than the sample size, but it's beginning to shrink. So this would be called the weak localization regime, where interference, self-interference effects become more obvious in your transport measurements. So the wave function would appear like a distorted block wave. Transport's most likely diffusive, but it still remains a metal because the wave function extends beyond the system. Now, as we increase the disorder even further, we enter this strongly localized regime. Here, the wave function is much smaller than the sample, so it can be purely described by this exponential envelope or a localized state. So here, transport is by another mechanism called hopping. So at high temperatures, I mentioned that inelastic scattering essentially breaks up localization. However, at low temperatures, when the bath energy becomes comparable with your energy level spacing of your discrete disorder states, you start to notice these localization effects. Hence why we perform these measurements at ultra low temperatures within a dilution refrigerator. So this idea of low temperature transport in a strongly disordered system was first developed by Professor Mott at the University of Cambridge. So he considered a relatively simple model where you have some localized state on some potential minimum, say, and it's trying to be transported to a site a distance r away. To do so, it has two mechanisms. It can tunnel through the potential barrier. This is a quantum mechanical effect, quantum tunneling, or it can interact with the bath and be excited to the nearby state. So these states will always be separated by some energy difference, W. I should mention also that these two mechanisms work in tandem with each other. You can't really have one without the other for a localized system. So what Professor Mott did was essentially express R in terms of W through things like the density of states and the impurity concentration, optimize P with respect to W, and by doing so, you return this very famous result where the typical hopping length, R star, depends on temperature. So this is quite surprising because you would assume that it would be easiest for an electron just to hop to neighboring sites and essentially chain up these hops until it left the system. However, you find that as the temperature decreases, the electron will hop very large distances. So this is called Weber range hopping. And it kind of makes sense if you think about it, even in a naive way. So as your bath temperature lowers, it becomes more energy efficient to hop to a state that's very far away but close by in energy, rather than a nearby site that may be far away in energy. So that's the general explanation of why Weber range hopping kicks in. So this process should continue down to zero temperature as the electron will hop further and further distances, and it shows up in your conductivity or the temperature dependence of your conductivity or resistivity in this case. One thing to note is that this power is quite important because it distinguishes not only the dimension of the system, so here D is 1, but also variations of Weber range hopping. So for such a simple explanation, Weber range hopping has been, or the theory of Weber range hopping has been extremely successful. So one of the earliest observations in experimental semiconductors, like the materials that we look at, silicon in this case, was performed at the Cavendish laboratory. So here you've got log conductance against T to the third. This is a 2D system, hence third, 1 over D plus 1, 1 over 2 plus 1. But it's also been observed in a variety of experimental systems. So example, gallium arsenide here. for a 3D bulk system, say a bulk crystal, and also more recently in our indium antimonide thin films. So this was a result published 2 years ago. So the work that I've been doing to kind of develop this field further is to basically suggest that there exists a new regime below variable range hopping called low temperature activation or simple activation, which has very unusual properties, uncharacteristic of a disordered system. So you can see this transition to this regime in this W plot. These plots are slightly confusing. They're the derivative of the log resistance with respect to log temperature. But essentially all you need to know is the gradient of these plots gives this value P. So at high temperatures, we observe this P to the third, so 2D variable range hopping. But then below a critical temperature, say around 10 Kelvin in this case, we observe P to the 1, so hence simple activation. So this has been observed in indium antimonide, the material that I'm going to talk about today. It's also been observed in graphene by my colleague at UCL. There's also results in yttrium silicon, so a semiconducting material, superconducting material, sorry. And there's also published results, for example, silicon boron here, gallium arsenide, and a very famous result in indium oxide, again, another superconducting thin film. So you can see this very similar behavior where they observe P to the third, and then some critical temperature, and then P to the 1, indicating this transition to this low temperature activated regime and this breakdown in variable range hopping. So we look at a variety of samples and a variety of methods to study strong localization. The first is in gated heterostructures. So these are typically relatively high mobility 2DEGs, so 2D electron gases. And then by applying a large voltage to a gate some distance away, separated by a dielectric, you can deplete carriers from the 2D system, which then lowers your Fermi energy into this localized band tail. So this is that advantages and disadvantages. One disadvantage is you're limited by leakage resistance to the top gate. And in a heterostructure, you're also limited by things like parallel conduction. So these samples are extremely resistive, typically 10 to the 12 or even 10 to the 11 ohms. So these small effects that you would typically ignore in 2D systems start to affect your measurements. So rather than using gated structures, we then introduce disorder using a variety of methods. One is with doping, but a more successful method was with this exposure to a focused ion beam. So this is how we studied the properties of disordered graphene, as well as the disordered indium antimonide thin films. So typically our films are grown by molecular beam epitaxy. They're typically either 20 nanometers to 300 nanometers. We're limited on the thickness of these films due to the growth properties. They tend to grow in clumps if you try and make a film less than 20 nanometers. And the wafers straight out of the growth chamber, so before we've introduced additional disorder, are already within this weakly localized regime. So disorder in these materials comes from two main sources: the interface roughness, so typically indium antimonides grown on semi-insulating gallium arsenide, which has about a 12 to 12% lattice mismatch. So this causes dislocations and interface roughness at the boundary between the indium and the gallium arsenide. There's also impurities from the growth chamber, which are essentially unavoidable. So it shows up even when we change chamber types. So because we're in this weakly localized regime, we observe a lot of phase coherence effects. So the contribution due to this self-interference, which I mentioned before. So one is a weak anti-localization magnetoresistance. So typically when you put a magnetic field on a weakly localized system, you destroy self-interference. So all those looping terms are destroyed by the magnetic field. So you would get an enhancement in your conductivity. But because there's also a strong spin-orbit interaction in indium antimonide, this effect is flipped due to additional pi phase shift associated with spin. We also see universal conductance fluctuations in very small samples. So again, this is essentially these self-interfering paths contributing to your measured conductance, which show up as something very similar to noise. We also see a temperature dependence in these samples due to the temperature dependence of the phase coherence length. So obviously a larger phase coherence length, the more these looping paths dominate. So as you cool down, you get this enhancement in weak localization. And in very, very clean samples, it's possible to observe a true metal insulator transition, typically observed in 3D systems. However, this was only seen in extremely clean samples not grown by molecular beam epitaxy. So to enter this strongly localized regime, we developed this ion damage procedure. So typically an ion beam or a focused ion beam is used for imaging. So they're very complicated bits of equipment, but if you characterize the beam correctly, you can resolve 20 to 30 nanometer features. So originally we were imaging our devices with a focused ion beam. Here's an example of an anti-dot array. But what we noticed was if we looked at a sample for more than a few seconds, they became unmeasurable at low temperatures, which obviously wasn't ideal. So we took advantage of this and developed this ion damage procedure, because it was clear that the ion beam was disordering our typically very clean semiconductors. So we generally make an array of samples, something like this, and then we would align the ion beam on one of these edge samples. So the edge samples are typically lower quality anyway, due to things like edge bead resists, which form during your fabrication stages. And also just due to the vicinity to the edge of the chip, which you have to scribe to extract. So we sacrifice essentially these edge samples and align the ion beam on these samples. We then attach a beam blanket, and as we know the dimensions of the array, say 1,500 microns in this case, we can blindly jump between samples and then remove the beam blanket in a very controlled way to perform our exposure. So this has been extremely successful, primarily due to the flexibility of the number of parameters we have to control. For example, we can vary the ion species. So for example, we've used gallium, neon, and helium. I typically use neon because it's a nice trade-off between obviously the mass of gallium and the lightness of helium. But we also have things like the beam energy. So we've got a maximum beam energy of 25 kilo electron volts. We can also vary this. We've got things like the beam current, but the main parameter that I used to vary or control the disorder was the exposure dose. So the number of ions that hit the surface of the sample per centimeter squared. So after this ion damage procedure, the sample properties changed dramatically. So now we're in this strongly localized regime, which I obviously outlined before. So now we don't see this quantum correction. Rather, we're in this strongly activated regime where the log of the resistance, this is a log scale, is proportional to 1 upon temperature. So very typical of a strongly localized system. For very high dosages, I typically observe variable range hopping. However, we found this very unusual regime, which is at relatively weak disorder, where we observe these strange phenomena. One being this quantized pre-exponential or semi-quantized pre-exponential here, this intersection. The next being this absence of variable range hopping at low temperatures, this simple activation regime. Also these hysteretic current jumps with applied voltage. Plug in my laptop battery. And also this overactivation effect below this critical temperature T star. So for this talk, I'm really going to focus on this absence of variable range hopping, this simple activated regime, and this these hysteretic jumps in current. So like I mentioned before, we observe in our samples this prefactor close to this quantized value h upon e squared, which is obviously very unusual, as you expect, given variable range hopping, that the prefactor would depend on the properties of the phonons, the lattice properties. However, it's extremely unusual this takes the quantized value independent of the materials, so different lattice properties. It always takes this universal value. I should mention before that this curve is calculated within the ohmic regime when the applied voltage is very small. Our samples are also squares, so this is a resistance per square. We also observe this 1/t dependence for over 4, 5 more orders of magnitude. So this is important because if you have a very narrow data range, it becomes very difficult to distinguish log rho versus 1/t to 1/t to the half, say. So to say anything definitive, you need this large data range in your measured resistance. Then as we lower the temperature further, we enter this saturation regime. So as we leave the ohmic regime, when the applied voltage is small, we enter this non-ohmic regime. So it was extremely surprising that as we increased the voltage, we observed these extremely large hysteretic jumps in current. So you can see this is lattice temperature, red being the hottest lattice temperature, blue being the coldest. And as you cool your sample down, you get this regime where your current, say at this point here, jumps to this much larger regime. So these hysteretic jumps depend on the sweep direction, say increasing applied voltage or decreasing applied voltage. So if I swept the other direction, these jumps would occur over here. They're also dependent on the lattice temperature, so the jump position varies as you cool the sample down. And also at very low voltages, we observe this linear voltage regime, where the log of the resistance, V over I in this case, is proportional to voltage. So to explain our observations made in our disordered indium antimonide thin films, we use this simple phenological model, where we assume a prefactor close to the quantized value, h upon e squared. We know we're in this simple activation regime, hence this p value is 1. So simple activation can be due to a variety of reasons. Most famously, a mobility edge. Any sort of gap in your density of states can lead to this effect. For example, nearest neighbor hopping, where you have this fixed range hopping distance. Things like a charging energy can also lead to this effect. A superconducting gap. Indium antimonide itself is not superconducting. However, indium is, which may be relevant for some of our observations. And obviously, there's more complex explanations, something like this 2D logarithmic Coulomb interaction. So we can rule out a mobility edge and nearest neighbor hopping because we observe this variable range hopping at higher temperatures. So these effects usually kick in at much higher temperatures than variable range hopping. And we can also rule out a superconducting gap based on the indium antimonide isn't superconducting. We then include two non-ohmic effects in our model First, this field effect, which accounts for the voltage due to the tilt in the potential landscape. So this tilt effectively lowers your gap size by this term alpha V. So this is actually quite nice because this alpha term provides information about the system, notably the typical hopping length A. We also include a voltage dependence through the electron temperature. So electron heating in metals and dirty metals is very common because the electrons can essentially drift in the electric field over large distances without interacting with a bath. However, in variable range hopping, you're constantly interacting with the bath through this inelastic scattering event that maintains hopping. However, we're making the assumption that this variable range hopping mechanism isn't working in the regime that we're in. So we assume we have this weak electron-phonon coupling. So by doing this, we assume that the heat balance equation used to describe dirty metals can be applied to insulators. So essentially you're equating with your power in, say your joule heat, V squared upon R, with your power provided to the electrons and then taken away by the bath. So unlike metals, a strongly localized system is strongly dependent on the electron temperature. So you get this very unusual feedback mechanism occurring where as your joule heat increases with applied voltage, V squared upon R, shown down here, and your electron temperature then increases, which then lowers your resistance significantly, which then comes back and increases your joule heat. So above a critical voltage, you get this very unstable regime where your electron temperature can very suddenly increase. So on the left is the measured current on a logarithmic scale versus our applied voltage. So the colored squares are the experimental data, and the red lines are the hot electron model given only measured parameters. So we obviously could do a global fitting procedure and fit these parameters, but I find it's more interesting to show how well the model does, even when we just plug in the measured values. So we extract things like the pre-exponential, the gap, the saturation temperature from the measured ohmic resistance. We can also plug in other constants from the linear voltage regime and also things like the electron-phonon coupling strength. And we find that this model works extremely well in describing our data, which is obviously very unusual for a strongly localized system. There's two areas that we still need to think of additional effects. The first is this secondary jump regime, where the model predicts that you should be temperature independent here. However, we still see this temperature dependence and also these secondary jumps. We also have an additional conduction mechanism coming in at very large voltages. So the prediction is less than what we experimentally measure. You can also compare the measured critical parameters, say T star and the V star, where the jumps occur, with the experimental data. And this works very nicely. We get this very nice trend between theory and experiment here. So the hot electron model can explain the jumps, but it can also explain the saturation within our system. So these curves are calculated within the ohmic regime when the applied voltage is 0. But in experimental systems, you can also have other factors which influence the electron temperature, most notably high frequency noise or radiation. So these are unwanted experimental effects that are typically very weak, that you wouldn't notice in, say, a good metal, which isn't very temperature dependent, however, show up very strongly in these localized systems. So if you go through the heat balance equation and then obviously ignore the joule term, then you find that your electron temperature follows the lattice temperature, but then becomes limited by the saturation temperature. So the saturation temperature increases with this background heating power, which is an umbrella term to include all sources of heating in the experimental system. And it also increases as your electron-phone uncoupling strength, this G term, decreases. So this has been also verified by experiments, as in samples with a weaker electron-phone uncoupling, say graphene, they saturate at much higher temperatures than the indium antimonide that I look at. You can also do things like improve the noise levels of your fridge. Recently, we removed RF lines that we think were adding noise to our experimental system, and we found that the saturation temperature of these samples decreased as this P0 value got smaller. We can compare our data with the field effect model. So this was this linear voltage term here. So one prediction is that the gradient of these curves, shown here, should be proportional to 1 over temperature. So the gradient is given by this value A, and this is 1 over temperature. And we see this very nice straight line, which is also encouraging, that this simple model can describe our data very well. The gradient of this curve actually provides information on the system, namely this typical hopping length, A. So it's very interesting that the typical hopping length is very large in this system, 700 nanometers. So it typically varies from 200 nanometers to 700 nanometers, depending on the amount of disorder we introduce to the system. So for context, in variable range hopping, this typical hopping length has been measured to be 20 to maybe 50 nanometers at low temperatures. So it's much larger than what you would observe in the variable range hopping regime. One thing we're still working on in this area is that we have this non-zero intercept. So it's very clear here, which suggests another voltage dependence that our simple model doesn't account for, perhaps a voltage dependence of this prefactor. So just to take a quick pause here. So far, we've observed this low temperature. I've described how we observe this low temperature activated regime in disordered indium antimonide. So we explain our effects in the context of hot electrons and also this field effect model. And our main assumptions are that the electron-phone uncoupling is very weak, and also we have this very large typical hopping length. We also assume noise in experimental systems to explain the saturation, but that's fairly justified. There's no ideal experimental systems. So the rest of our observations, namely this absence of variable range hopping, all tie into this granularity model, which is still something that's being developed and worked on. So the main assumption of this granularity model is that at low temperatures, you get these effective grains forming within your system. So instead of hopping between disordered sites, you now get hopping between these grains. So these are metallic grains within an insulating sieve. So rather than the gap energy being set by the disorder, like in variable range hopping, they're now set by the charging energy of these grains. So we assume that these grains are very large, so that the average energy separation within the grain is very small. So if we decrease the grains, this energy level separation would increase until you get something like a quantum dot. But these are very large, so we don't need to worry about things like this. But what this tells us is that there will always be an energy level within a neighboring grain that's nearby. So you don't have to jump very large distances to find a nearby energy level like you do in variable range hopping. So this explains why we see this simple activation rather than variable range hopping, because the electron is just hopping between nearby grains. So the typical hopping length here would be given by the average grain separation, which obviously has to be comparable or larger than the grain size. So it should be quite large. Phonons should be weakly involved in the transport between grains because these energy levels are so nearby in energy. However, relaxation occurs within the grain. So you get the separation between transport and relaxation. hence why we would observe this weak electron phonon coupling. So we can make three predictions of this model. The first is that the Tibble hopping length should be large because it's given by this average grain separation, which we know to be true already, typically 600 to 700 nanometers. T0 should be related to a charging energy rather than a average energy distribution due to the disorder. So we can make a very simple approximation of this by assuming T0 is given by E squared upon 2C, so a charging energy, and we assume a capacitance associated with spherical grains, and then we compare that with the measured value from the linear voltage term. So the linear voltage term is given by these red circles, and the grain size is given by these blue squares. So we see this nice correlation between the two, which is encouraging and in support of this granularity model. This granularity model also relates to secondary jumps, which we observe in our sample. So we've been fabricating these samples, which are quite interesting because they're essentially a single hole bar that decrease in size as you move down the hole bar. So this top sample here, apologies, it's quite small, would be 200 by 200 microns and 100 nanometer thickness. And then as you move down the sample, you move to this sample, which is typically 5 microns by 5 microns. So as it's all in the same hole bar, you can damage the whole sample in one go using the ion beam. So you don't get this disorder variation between samples. So this is currently a project that's still ongoing. So one big question would be, what is the origin of these grains? So to us, there's two main mechanisms: physical grains, something like a phase separation between the indium and the antimony. So this would have to be present in all MBE grown indium antimonide wafers grown on gallium arsenide. And it's very likely that this ion beam damage procedure may enhance this phase separation. So if you imagine a situation where you're knocking off antimony atoms, which then manage to group together, forming this indium-rich phase. So this supports other observations we make, like this overactivation, which has been linked to superconductivity. And there's also some X-ray diffraction evidence. So this is an X-ray diffraction plot, and each peak corresponds to a material trace. So we can see peaks for the gallium arsenide substrate, the indium antimonide thin film, but we also get these very weak peaks corresponding to indium. So that's one explanation. Another explanation is slightly more complex and relates to pseudo-grains, which occur in systems with a very large localization length. In these systems, the electrons are slightly more mobile because they behave more like a metal, say, which effectively screen the electron-electron interactions, giving it this long-range character. It's got this additional logarithmic term. So these longer-range Coulomb interactions can be modeled as effective grains or pseudo-grains. So this would be more likely in materials where phase separation is impossible. For example, graphene, where we observe very similar effects to what I've talked about today. So this is a model really developed by our colleagues at the University of Murcia in Spain. Okay, so I'll just give a very brief summary. So the work that I've been doing at UCL is looking at these disordered semiconductor systems, typically indium antimonide thin films. And what we noticed was that for weaker disorder, we observed this absence of variable range hopping and instead this simple activated regime. Along with this came these large hysteretic current jumps, which we modeled by this hot electron model and the field effect model. So inbuilt in these models is weak electron phonon coupling and a large Tibble hopping length, which points us in the direction of these granularity models. So there's obviously still a lot of work in this project to do. We're interested in this secondary jump regime, which I briefly mentioned, and also things like this overactivation, which I didn't discuss in too much detail. So this is not just a unique effect in indium antimonide. It's been observed in a variety of materials, mainly superconducting thin films, but also, like I mentioned, gallium arsenide and graphene. So if you are interested, you could probably do some research related to these materials here. Okay, thanks a lot for listening, and I'll happily take any questions if you have any.
Thank you, Johnny. That's very nice presentation. What we traditionally do is we ask the panel members to formulate questions. I've had a message from Arturo. Arturo is in Mexico. He's said, thank you very much. He doesn't have any questions for you. He says, thank you for your talk. I would like to ask other panel members. Let's perhaps start with Gabriella. Gabriella, do you have a question for Johnny, please?
Hello.
Hi.
Should I? Well, I was wondering, because I didn't start from the beginning. I was wondering if there are other experimental techniques to compare, and you showed the last picture in almost your last slide. If there are, I was wondering if there are other experiments to compare or to add to your picture, no, to this picture. Like
Yeah, so obviously we're very limited by transport measurements, because they obviously give you a global picture, essentially the average over the entire property of the system. So you need a very local measurement. And some of my colleagues in University of Paris-Saclay do these low temperature AFM, conductive tip AFM measurements, where they essentially scan the surface of the material and they look for essentially evidence of these grains, these high conductivity regions, compared to this background insulating regime. But no, within our lab, we're essentially limited to transport. We're also performing thermal power measurements on these samples, because obviously we have this weak electron phonon coupling. So you should have this weaker thermal transport within the system. So yeah, that's the main way we're kind of probing these materials. But no, it's a very good question. And like I say, you are limited with transport because it gives you this global picture.
In transmission electron microscopy, is possible to add some information? I wonder.
No, absolutely. Yeah, absolutely. We actually think in some materials, say if you get this phase separation and these indium grains go superconducting, that was one approach that we were attempting to do, because you would see this very large signature because it's superconducting at low temperature.
Okay, great.
No,
Thank you very much. I like your subject, this subject, your talk very much was very good, very nice.
No, thanks a lot.
I'm also curious about how this connects with qubits, but
Qubits.
I don't know if you want to go there or yes.
Yeah, I'm not
you can go
sure.
to the other talk, the other questions.
Yeah.
It's a curiosity.
Yeah.
Thank you, Gabriella. Did you conclude your question to Johnny, or should we discuss the qubits? Maybe in a future
leave
talk.
it to you.
Maybe in a future talk we can discuss.
In the next talk, yes, we
Thank
can
you.
study about qubits.
Thank you, Gabriella. I will ask. Thank you. I will ask now Ximena. Ximena, do we have any questions from your network, please?
Okay, thank you for your talk. No, we don't have any question from here, our National University of Colombia. The people only say thank you for your interesting talk. And thank you so much for all these process and these methods in your samples.
Thank you.
Thank you, Ximena. We also have James. James, do we have any questions from your network, please?
Oh, no, profesor, solo hay felicitaciones por la charla del profesor.
Thank you. James says thank you, Johnny. Thank you.
Thank
Oh, we also have Henry Moncada from Lima. Henry, would you like to ask a question, please, to Johnny?
Hi, nice presentation. Well, these fields are all my fields, so but I'm curious about when you in your one of the graphs, the one also the one appear in the slide for the presentation. You use a computational tool, right, to basically mimic the experimental results. So I was wondering, what is the name of the tool that you use?
the model
Is
to
Yeah, the one that also appeared in the one of the I mean in the presentation slide. Yeah, that one. So I mean so yeah. So I was wondering. I mean, what is the name of the tool that you use? So I mean, there's people involved.
So this model is called the hot electron model. And it was something you'll be able to find it because it's obviously not applied to localized systems very often, but it's often applied to metals and dirty metals. But in the context of disordered systems, if you Google Boris Altshuler, he's the one that originally kind of developed this field. But it's called the hot electron model. When you include additional voltage terms, it's called the extended hot electron model. So this is just an overlay of the model onto the experimental data.
Okay. Thank you for answering my question.
Yeah, no worries. Thank you.
Thank you, Henry, for your question to Johnny. I think that is everybody. I mean, I could ask a question, but I'm involved with the work. Maybe, Johnny, you could just mention the equipment that you would use for measuring 10 to the minus 13 amps. It's a very small current. Perhaps just mention the equipment you would use for doing that.
Yeah, no, absolutely. So obviously this was one of the biggest challenges for the first couple of years of my PhD because these samples are so resistive. They can be gigaohms or even slightly higher. So at very high resistances, you're very limited in what measurement circuit you can do. For example, the capacitance of your system becomes comparable with the capacitive part of your circuit becomes comparable with your measured signal. So this kind of rules out AC, which obviously scales with your driving frequency. So the main way of doing this is with a two-terminal DC measurement. So obviously two-terminal measurements are not as ideal as a four-terminal measurement because you get things like contact resistance and series resistance associated with the leads and the wiring. However, these samples are gigaohms, so a kiloohm, say, from the wiring is not a big contribution to your resistance. So two-terminal measurements work very well. You can either source current or source voltage. So if you're sourcing current, you essentially have to charge up your capacitive part of your circuit. So it's got this very long settling time. So instead you apply a voltage and measure current. And essentially it's the only way to do these measurements with equipment with a very high input impedance and output impedance. Otherwise you're just essentially measuring your instrument. If you have a megaohm input impedance and you're trying to measure a gigaohm, then the current will just go through your instrument. So you need some things with a teraohm input and output impedance to measure these things. But no, it's a big challenge.
Thank you, Johnny. We traditionally at this point ask if you have any general comments that you want to make public to the network, or any comments, any kind of a conclusion, any comments you want to make to the network?
Yeah, I guess, if you are interested, my email's here, so I'll happily provide the slides or even my references. Obviously, I enjoy talking about this stuff, so please contact me if you have any further questions. We're going to publish some of these results very soon, so keep an eye out for that. You maybe see my name on the papers. And yeah, no, thanks a lot again for the invitation to talk about the subject.
Okay, thank you, Johnny. Traditionally, we ask people to share their cameras and we can wish you goodbye. And thank you again, Johnny.
Thank you.
Thank you for joining us, Henry, this week.
Thank you, everyone, for this
Thank
talk
you,
of
Ximena.
this
Thank
week.
you, James. For,
We will see you next week.
next week. We see you next week.
Adiós a todos.
Yeah.
Goodbye.
Have a good day. Bye. Thank you, Gabriela. Bye, everybody. Good
Bye.
luck in Spain, Johnny.
Thank you.
Adiós a todos.
See you when you return.